Hi guys, let's play some math games. In this topic, I'm going to talk about the relationship between 1 and 0.9 repeating. Some of my friends just told me, oh, 1 is greater because 0.9 is approaching 1 but never reaches 1. So 1 is absolutely greater than 0.9 repeating. But the answer is no, you're wrong. The relationship between them is equal. 1 equals to 0.9 repeating. Why? If you're searching online in Wikipedia or some other websites, you may find some complex proof for that. It's quite complex. You can find the answer absolutely, but I'm going to give you some simpler way to prove this relationship. Here I'm going to prove this relationship between 1 and 0.9 repeating in two methods. The first method is quite simple. But first thing I'm going to do is to write the 0.9 repeating into an actual way, because this 0.9 repeating has infinite nines inside this digit. You cannot count out how many nines it has. So I have to write it into an simpler way, but more actual way. So it's just the 0.9 repeating. Let's write it here. It can be written as 3 times 0.333 and repeating. So this 0.3 repeating, you might have a kind of sense that it's just a 1/3 is a fraction. So for a fraction, it will be more actual for you to recognize. At least you can write it out what it is. So 3 times 1/3, it will be just 1. This 2, 3 will be cancelled. So this is a kind of simple way. I name it as method 1. But more specifically, you might not be satisfied with this kind of simple proof. So I'm going to give you a more specific one. I name it as method 2. Method 2, I'm going to write this 0.9 repeating into a way that gives more information about its property. So we know that 0.9 repeating, there are infinite nines inside this digit. So we just write them out. It's 0.9, right? Plus 0.09 plus 0.009 plus dot dot dot. You don't know how many how many digits in between the first and last. So we just say they are infinite with the last. What is the last? 0.00 dot dot dot. We don't know actually how many zeros there are. So there are also infinite zeros in between. So in this way, that we still have no idea about the whole thing. Is still is so great. So we try to write it into a more actual way. 0.9. We just try to use the same method in the method 1 to write it into a fraction. So 0.9 is 9/10, right? 0.09 is 9/100. And the third one is 9/1000. And I'm sorry for the shifting. And there are infinite things. So I'm not going to write all things out, but the last one, you have 9/, just 10. Nope, there are infinite zeros, right? Dot dot dot. So here are infinite zeros. Still not you want to write it in infinity, or you just write as infinity minus the 3. It doesn't matter because they're too great. So we just write it in this way. But they're still not actual. But we easily comment that 10 is just 10, right? But 100 is 10 times 10. So 100 can be written as 10 to the power of 2, means 10 squared, and 9 in numerator. The third one is 10 to the power of 3, and the fourth one we know Yeah, definitely it's 10 to the power 4. And dot dot dot, there are so many terms in this circle sequence, right? It's just a sequence. And the last one, is 9. And there are infinite 10, so we gotta write it out as 10 to the power of infinite. But this way, I can't say this way is wrong, but let's write it more specifically and more professional. So this 9 mean 9, we get all the 9s out from the sequence. It will be 9 times a 1 over 10 plus 1 over 10 to the power of 2 plus 1 over 10 to the power of 3. That is 3. Sorry. And 1 over 10 to the power of 4 until the last one, which is 1 over 10 to the power of infinite. But this infinity, I'm going to substitute it as n, and this n, I'm going to use an approximation. It's approaching infinity. This way will be, more professional. And we can just write this n to the power of n approaching infinity from the bracket. So with all those things into something like a 10 to the power of something, such as 9 times limit n is approaching infinity, right? We just shift this out. So the first term will be a 10 to the power of -1, right? 1 over 10 is 10 to the power of -1. The second term is 10 to the power of -2 and 10 to the power of -3 and dot 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 dot. I don't know how many terms it has. So the last term, it will be 10 to the power of -n. We don't need to care about this limit thing, but we need to simplify all the things here. We still cannot write the whole thing out, so we have to find a simpler term to represent the whole thing. It will be a geometric sequence or geometric progression, as you like, but I'm going to talk about it as long as we need this knowledge. So now let's talk about geometric sequence. We have to use the result of what we got above. It's something like this, and we can find out the second term will be a multiplication with the first term with 10 to the power of -1, right? And third term and second term, we can also find this kind of relationship. It times the same thing, we got the third term, and times the same thing, we get the fourth term until the last. So in geometric sequence, we have to have a relationship between the first and second, or the second and third, which means the two adjacent terms, right? So, and all of the relationship here is just about the same ratio. It's named as common ratio, right? So I'm going to write this thing out, which is A2 is Q. Q is the common ratio, right? Q times A1, and A3 is Q times A2. Sorry, it's times. And this footnote 2 and 3 represent the order of the term, or you just know the second term, the third term, and the first term, right? And we know that the second term here is also a multiplication of Q and A1. So we substitute this A2 with this. We got Q times A1, which means Q squared A1, right? And we also write A4 out is Q times A3. So it's q times q to the power of 2 n times a1, which means q cubed a1. So this is the relationship. And with this kind of regulation, you can also get the fifth term, and I don't write them out, I just write the last, right? The last will be q times a n minus 1. So I guess write the thing out. You can find that a3 is 2q's multiplication times a1, and a4 is 3q's multiplication times a1. So for the last term, it will be how many terms of q's multiplication and times a1? It will be q's power of n minus 1, right? Because they are, just observe here for q2, a2 and a1, sorry, a2 and a1, there's q's power of 1, right? For a3 and a1, there's q power of 2, so 1 plus 2 is 3. And here, 1 plus 3 is 4. So for the last term, it's just 1 plus n minus 1 is an, is this n. These are the relationship. All right, we can write out all things out, but what we need is the summation, right? The summation of all the terms a1 until an. So we write in summation as an, we name it as n. It's a1 plus a2 plus a3 plus a4 plus dot 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 until you got a minus 1 plus an, right? Because you note the as n has the summation of all, so there are n terms, last term will be an. And in this way, we still have no idea what's just like after the summation, right? So we need to do some observation. Let's look at what we have here. a2, a1, their relationship is just q, right? Adjacent term has a common ratio q. So a3 is q times a2, a4 is just q times a3. Adjacent term has a common ratio q. So for this summation equation, we also have to use a q here, make use of q. We can write this relation out, right? a1, we got nothing to say, but a2, right, is just q times a1, right? a3 is q times a2, and a4 is q times a3, dot dot dot. an minus 1 is q times an minus 2, right? And this an is just q times an minus 1. The relationship between a2 and a1 is just 2 times a q. So I write all things out. The next, we do some observation. We know that all the terms are with q, you see? It's a1 times q, a2 times q, right? a3 times q until the last term, right? q times a n minus 1. So we observe this thing, and we get this q out. It's just a1 plus a2 plus a3 plus a4 plus dot 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 plus an minus 2 plus an minus 1, right? And it looks so similar to this one, this equation, which is as n. What's the difference between them? It's just the last term, right? So I'm just going to write it into this way. It's a1 plus a2 plus a3 plus a4 plus dot 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 plus an minus 1, the last term, but without this an. but we still need it, right? So we just write an and minus an to compensate the thing. So easily we get a1 plus q times the whole thing here. Let me use another color of pen. This whole thing here is just Sn, right? So it's Sn minus An. It's more specific. At least you write something infinite into something finite. Then we're gonna do something like we shift this Sn to the same side. So this equation will be Sn, we shift this to the left hand side, minus a1 equals to q times Sn minus an. Okay, we shift the whole thing here in a new page so everything will be clear. Then I kill this bracket. It's q times Sn minus q times an. And we shift this term to the left hand side. It's 1 minus q Sn, right? These two terms, I contain them into here. And I shift this a1 into the right hand side. It's a1 minus q times an. So Sn will be a1 minus q times an over 1 over q. Wow, it's much more specific than actual. That's what we need. So with this relationship, oh yeah, we still gonna have to get this an. What is an? An is a1 times q to the power of n minus 1, right? We substitute this an with this. We're gonna have Sn equals to 1 over q a1 minus q times an is this a1 times q to the power of n minus 1. So it's a1 again times q to the power of n minus 1. Then 1 over q a1 and this multiplication. So it's a1 minus a1 times q to the power of n, right? And we get a1 out. 1 over q, which is 1 times 1 minus q to the power of n. And eventually we get a1 times 1 over q as denominator and numerator to be 1 minus q to the power of n. And this is Sn eventually. So everything here, we can use it to solve our equation above, which is something like 10 to the power of minus 1 minus 2. Alright, let's move back to our original equation. We know that the thing that we need to solve is 10 to the power of negative 1 until 10 to the power of negative n. And let's substitute all the things with this equation. What is a1? a1 here will be this 10 to the power of negative 1, right? Q, this a1. And what is q? Q will be also 10 to the power of negative 1, right? N, as we don't know, so we just write it as n. So this case, 10 to the power of negative 1 plus 10 to the negative power of 2 plus 10 to the power of negative 3 until 10 to the power of negative n will be a1, which is 10 to the power of negative 1 times 1 minus q. Q is 10 to the power of negative 1 with 1 minus q to the power of 10 to the power of n, right? So q is 10 to the power of negative 1 with power of n. N, we have no idea how many it has. So we do something to simplify, which is 10 to the power of negative 1 is just 0.1. And this is 1 minus 0.1, right? So 1 minus 10 is 0.1 to the power of n, or just 10 to the power of negative n, right? Negative 1 times n. So we're going to have 0.1 times 0.9, 1 minus 10 to the power of negative n. And we know that 0.9 repeating is 9 times 2, and n is approaching infinity with the summation of the whole thing here. So which means there what we need to input is the result of here. So it's 0.1 times 0.9, and what's above 1 minus 10 to power of negative n as the whole thing, and do a limitation and do approaching for n to infinity. Then we can multiply this 9 and 0.1, right? So 0.9. We shift this out. It doesn't matter. It doesn't affect anything about this limit. So it's 0.9 and limit n to infinity. Here, denominator is 0.9 and denominator is 1 minus 10 to the power of negative n. Still write it in this way. So, well, it's quite good. We can cancel this to 0.9. So what we got, a limit n to infinity, 1 minus 10 to the power of negative n. And we know that 1 has nothing to do with n. It doesn't contain any term that has relationship with n. So we just shift it out of this limit. So it's just 1 minus limit n to infinity and 10 to the power of negative n. We draw brackets. To clarify, I use a blue pen. This is the result we got. So now we are going to do something about this 10 to the power of negative n. When n is approaching infinity, what to do? All right, for this 10 to the power of negative n, we do a limit for itself. Then we actually get no idea about how this n affects the whole thing. But we know that there is something we can do about it. It's just to simplify. So we simplify the whole term into this way. It's 1 minus next limit n to infinity, 10 to the power of n with 1 in denominator. So we know that this is a fraction, right? So we just do further simplification. It's just 4 10 to the power of n, and with the whole thing to the power of negative 1, because 1 over something is always a power of negative 1. It doesn't matter about it, or just write it this way. It's more specific. When n is approaching infinity, how about the 10 to the power of n? We actually we can draw a graph about it. It's n for for x-axis, and for y-axis you have 10 to the power of n. And when n is 0, 10 to the 0 is 1, right? When n is 1, 10 to the 1 is 10. So we have 2 points. When it's 2, it's 100. And when 3 is 1,000, even is 1,000. So draw something we can find. It has a tendency of all the way going up. So when n is going to infinity, this 10 to the power of n will also be going to infinity, because they all become very great. This one goes to an extreme, so this one goes to an extreme as well. Then the whole thing we can write as 0.9 repeating equals to 1 minus 1 over this thing is infinity. But we still have not got an answer yet, right? Let's look into this term. It's quite similar to what we have already learned as y equals to k over x, right? In this case, we know that k is 1. And we draw this y equals to k over x. We have learned before in secondary school. Something like this. We don't need to care about this part, right? We just need to care about this part. When x goes to infinity, which means all the way to there, this curve goes to a tendency approaching all the way approaching x-axis, as long as extending to infinity. This one near and near and near and near and near and near, but never never intersect with x-axis. But when x goes to this extreme case, this will also goes to an extreme case. So this term will be going to 0, because it's all the way approaching all the way approach 0. So eventually we got 0.9 repeating equals to 1 minus 0, which is just 1. This will be the result.
Hey guys, we're done with the solution. If you have any questions to discuss with me, or you want to share some idea, you can just leave me a message or just comment under the video. Hope you guys like my video. If you like it, please subscribe my channel. See you guys in the next video.